Whoa. Whoa. Yikes. Oh, maybe it's just me. Stay. Come on back in. Maybe the effect was just on me. All right. Well, hey everybody, how you doing? Welcome back to Physics with Dr. T. And today we've got Math Bar joining us. We're going to do some brand new physics that for the semester, which is looking at the wave nature of light. Light turns out to have both wave and particle characteristics, and for the next couple of weeks, we're going to explore the wave nature of light. We're going to start out with characteristics of light that we can use to test this, which is referred to as diffraction. And this diffraction uses interference. Before we get into the actual experiment, let's talk about this week's pre-lab activity. In this week's pre-lab, you'll first be asked to watch a segment of a walkthrough video I produced for another lab, which you can see here, in which the behavior of waves, including interference, is demonstrated. When you arrive to lab, I will demonstrate the interference using the same lab. You'll see the constructive and destructive interference. Before we proceed with lab, this will be all part of your pre-lab experience. By the way, when watching the Waves on a String video, if you skip to the bloopers at the end, you'll get to enjoy my youngest unique brand of adorable and amusing. So, for the second part of your pre-lab, what you need is just a simple geometric shaped dish, pan, tray, even a sink, what have you. And just a little bit of water. You don't need too much. If you have too much water in there, actually it will other effects will start to overplay. And we just are looking for some simple evidence of geometric reflection of waves off the surface and that there's interference. So I've got this object here, and I'm just going to use a can. I'm going to bounce it into the water at a regular pace. And what you're looking for is this area right here. You're starting to see some sign of that. That will do the trick for your pre-lab, and you'll have demonstrated interference, wave interference in water, and that should refresh your idea about wave interference ahead of the diffraction lab. And so in order to talk about these concepts, I'm going to turn this over to Math Bar, and he's going to talk a little bit about the theory that we're going to be exploring. Math Bar, go ahead.
Okay guys, so this guy, Huygens, try to figure out the wave nature of light by using this demonstration. So you can see in this figure the point source act is the source of the waves. So from every point source, the wave goes outwards, making a spherical wave front. So once the plane wave move on, during the course of that plane wave, if we choose a point, then this point can act as a point source. So this type of point source, during the course of time, they move with the same velocity of the wave front, and they will create a wave front. And this is the way the wavelets, the wave front move. So practically, or you can say that experimentally, when the wave front will strike, when the very small hole or the sharp edge, that will also act as the point source, and the spherical wavefront will create from them. So if two or more than two of this kind of spherical wavefront will combine with each other, then an interesting optical phenomenon happens, and that is the interference. You can see over here. So if we assume two wavefront A and B with similar amplitude A, when they will combine, when they are in the phase, the constructive interference takes place, and their amplitude will sum up and becomes twice A. In this similar way, if the two wavefronts are in out of phase with the same amplitude, they will sum up to give the zero amplitude. It doesn't mean that the light has gone away, rather the light has a zero amplitude over that space.
Excellent. So now that we've talked about Huygens principle, wavelets, and the general idea about waves propagating from certain points, we can start talking about what's going to happen with the light as it passes through your diffraction grating today. By the time you start working on your lab activity, I'll have demonstrated single slit and double slit diffraction, where you're looking at diffraction from a single slit or two slits that are close by to each other, and demonstrated that for you to see that they have a diffraction pattern. It spreads out from the point that you would expect it to, demonstrating wave behavior. But now we can look at what's going to happen in your physical setup. So you'll have your diffraction grating, which we've got kind of blown up here. And you can see the individual slits there through which the light's going to pass. Here comes the light coming over here, and then they form wavelets that expand outward. And what happens is you've got so many of these so close to each other that the waves will interfere constructively and destructively collectively, so that the only constructive interference that we see will happen at regular spaced light points, and in between it will be completely dark. So we won't see the same diffraction pattern as we would from a single slit or a double slit in particular. So here we look at the geometry. We say, what is a way of connecting the wavelength of the light that's coming in to the geometry and the dimensions that we have here? And we do so, say, here's a triangle for a beam that's going here to our first order bright fringe. So the geometry is this. We've got the triangle, we've got some angle relative to the center line that goes to that position. We've got some distance, y sub m, that goes from the center line to that first diffraction, second diffraction fringe. And then the distance between the diffraction grating and the screen that you're projecting on, given by the letter L. Now, the relationship between the angle and these dimensions is fairly straightforward. It's your tangent of theta, or the inverse tangent of your vertical and horizontal distances gives you the angle in between those. The spreadsheet that you have will do the calculation for you, provided that you give it the length L between the screen and the diffraction grating, and you enter in the y sub m for each bright fringe that you see on your projection screen. To take a closer look at what's going on over here on the screen, we need to take a closer look at what's actually happening over here trigonometrically at the point where the light diffracts. So here I've got us zoomed in on one particular slit within your diffraction grating, and you can see there's some space where their light's not supposed to be able to pass through on either side of it, and the width of that slit is given by the dimension d, lowercase d. On your diffraction gratings, you will have a line density, lines per millimeter. Well, the distance here is going to be the inverse of that. So whatever your line density is, you put that number in, and the calculation in Excel will give you the inverse of that and give you that distance d, how many millimeters per line, whatever the distance is for that gap. In order for there to be a bright fringe, we have to have constructive interference right at that point on your screen. In order for that to happen, the light from one end and the light from the other side of that distance have to arrive in constructive interference. So the only way that that can work is if the distance between here, the difference between these two paths, is some multiple, some integer multiple of lambda. So I've got this triangle drawn right here, where we've got the angle here, side here is slit width d, and this little difference of the two pathways, delta, must be some integer multiple where m is 1, 2, 3, 4, 5, 0 of the wavelength, the actual wavelength of the light. Otherwise, it's not going to be a constructive interference, it'll be destructive interference and won't be seen. As a matter of trigonometry, the length of this side, if you look at this, you'll see that from trigonometry definition of sine theta, this sine theta is the distance here divided by the hypotenuse, which is the slit width. So this is rearranged in such a way so that that differential distance, that differential distance is isolated on one side. So we can set these two equal to each other, eliminate the path difference, and then that allows us to state, okay, the fringe order, which is your number of fringes away from the center, times the wavelength is equal to this relationship, the slit width times sine theta. What is the unknown here, or what is it that we'd like to test this against? We'd like to test this against the wavelength, which we can extract from the optics, and so lambda equals these characteristics of our setup that we are going to use. M is going to be a 0, positive 1, positive 2 for going one direction, and negative 1, negative 2, and so on going the other direction. But you don't have to actually worry about that. Here's why. Just as these are negative fringe orders, these is also negative y along this vertical axis. So these are positive y times positive orders. These are negative y times negative orders. This should be symmetric anyways. So in practice, you're not going to need to worry about negative signs, just worry about absolute distances from your center point. So make sure you mark that center point when you put your laser in place, and then put your optic in, and then put your diffraction grating in place, and go from there. For this week's lab, you'll be using a laser beam, pass-through, and interference diffraction grating, and projected onto a screen, demonstrating the wave nature of light. Now, one of the key tools in order for do this is diffraction gratings, which are basically sheets of plastic that have been machined in such a way that there are tiny grooves or cuts in them as though they are slits, and those slits are spaced in such a way, in this case 80 of them per millimeter, so 80 within 1 millimeter, and then 100, 300, and 600. This one is 13,400 lines per inch, but once you convert that to centimeters, remember it's 2.5 centimeters for every inch, then the number works out to be around the upper 500s, 570, 590 lines per millimeter. And so light will pass through these and be refracted, and we can demonstrate a little bit. If I use my phone light here, you can see the center point there is the brightest one, and then you can see evidence of diffraction that's reflecting to us, that's bouncing off of these slits and then coming to the camera, in this case the camera's eye, and this should match what you see in demonstrated in lab. But the same effect is happening as it passes through this. The laser lights will pass through these and then go to the other side. A couple things to keep in mind. Please don't touch the plastic, because the fingerprints can disrupt the image that you're trying to make and reduce its clarity. Second thing is also it can change the orientation of some of these screens, especially on these cardboard frames. Next, in order to support this on the optics track that you'll see here in a few moments, we have this blank that has screws in it. So this is an optics blank, and what you'll need to do is unscrew a couple of these far enough. Place your grating onto the open space where you've got a groove for the screw threads, and then give it a snug tighten. Don't over tighten it. You can bend this forward as a result of that. So this basically now is diffraction grating is effectively at the same position as the front edge of this blank, and so don't use this position. This will be pointing to your values on the track. Make sure you account for the front edge of this when you're making your measurements for the position of the diffraction grating. You'll notice that this has a wing that has a little flexibility. Try not to put too much pressure on it. Set these into place. Just put it into the track and then snap it into place. It should be fairly good. Other than that, please try to handle these with care. And while you can make observations with just standard light sources like we did for the previous two labs, in this lab we're going to use some of the best quality light sources, which is column A light, aka lasers. So we have two laser sources here. One is red, one is green, and you can tell them apart because of the length of the nozzle or the extrusion here on the frames. They are labeled according to what color they are here at the top, and if you flip them over, you'll have more information to work with. For example, we have here a green laser with a wavelength of 515 nanometers. You also have a couple of controls. This will control the movement of the laser beam, or the alignment, if you will, on the track. This is vertical adjust, so it'll move it up and down. This is horizontal adjust, so it'll move it left and right. And then you've got your power source and the power control. Please remember, to get the longest lifetime out of these, we want to have the power off anytime you are disconnecting or reconnecting power. And so you plug that in, and then you press power, and you see the light comes on here, and it'll look probably discolored in the video here, but it's green. And then we turn it off, disconnect. You can also test the red, plug it in, turn it on, and then you've got your red laser beam. And so this is the proper care of these for best purposes. Let's take a look at these in place. In this week's lab, your lab setup is going to be somewhat similar to that you set up for your optics bench. You've got the optics bench here itself, which has got a metered measuring tape along the side, In this case, we have the target screen, but instead of using it as a target, we're now using it as a projection screen for the laser beam that we're working with that you saw in the equipment. Plug this in, set here, let's turn this on. So I'm going to start with the red light. And I have this set up in such a way that, as it turns out, I'm walking into this equipment having not tested it, so I wanted to, this gives an opportunity to take a look at something. You'll see that the red light shows up here on the screen, and I'm going to dim the lights here in a few minutes for us to see that. But then what I'm going to do is I'm going to adjust these two knobs that are on the back side of this, as I talked about. So I adjust this, and you'll notice the top one moves it left and right, the bottom one moves it up and down, but we're not too worried about the up-down in this case. There's no reason to limit our up-down. This is just to make sure that our left to right falls along so that the beam lies along a center beam path. This ensures symmetry as we mark across the surface. Now, I would like to take a few moments and demonstrate to you that there's a couple parts of this we need to be careful about and which ones don't really matter. You'll see here I've got the light source. This is the diffraction grating in place, and then this is the screen that's projecting on. And what I'm going to do is I'm going to move the laser beam source, and I want to observe what happens to this. And as I move this left and right, just sliding up and down, you'll notice that aside from shifting because of smoothness, it's not actually changing. There's no change in the distance between these faint red dots and the center red dot. However, if I move this, you can see they're coming in closer and closer. And so the length that you're interested in is actually this distance here. A couple of things about the setup before we get started is that you'll see that there's a meter stick that's been taped to the back of this projection screen, largely to give stability to this poster board that's been coated with packing tape because it's fairly erasable. But this allows you some stability and sturdiness as you go and make markings along the distance. So you'll make this measurement of this distance. This will be your length, capital L. And you'll measure the distances between each of these dots that you see that you mark on the screen. Those are the Y. So you'll have your triangle here where you have your length L from the optic to the screen. That's L, big L. And from this center dot, this center bright spot, to each bright spot you see is subsequent Y sub m, Y sub 1, Y sub 2, Y sub 3, measured from this as your 0. Once you've made the marks, you simply gently remove this and then get your meter ruler out, secondary meter stick, measure from the center. This is 12.2 centimeters. This is positive and negative. This one's 12.05. And so here I go into the file. I'm going to go ahead and so left and right, positive 12.2 centimeters. And this one was 12.05. Oh, where's it going? See, they stayed, in this case they stayed div zeros because I had not put a piece in there. And this calculation requires a length measurement. So we'll go back to the screen here and we see from the screen, which as long as you don't adjust it, should be 0 to 32.7. I'm going to modify this so that it'll actually, it's going to be this way. This will be modified. When you guys see it, you'll see this reversed. And now we've got some results coming in. We haven't told it what the laser wavelength is, but we're going to see if we can get some other data points in here. So that's going to be, let's see, do we have any secondary points? I don't think so. They were very faint. Let's say that you don't get enough data points and you still need a couple more just to get a good fit. What you can do is move it in closer. So I've zoomed in, and for this particular setup, there's just not enough. There's just not enough data points. So we're not going to be able to use that to do anymore. We just have those 3. So in that case, since we cannot get any more, we'll just come in here and we delete in the wavelength or nanometers column. So we delete those out of the calculation. That gives us about 717 for the red laser beam. And if you look at the back, just like I showed you before, you look at the back of your optic, it'll say 650 nanometers in this case. Double check yours to make sure that's right, 650.0. And then you see we've got 36.49% error. Laser comparisons, nothing yet. We'll see how things go. So I'll move this back to here, for example, back to about 33.75. That's about where I had it, right around there. Doesn't have to be there. It's just I'm just setting it back for your reference. Now I'm going to turn this off, and I'm doing this so you can see the red green. You just repeat with the red, go all the way down to different sizes and adjust your screens accordingly, and then you go and do the greens, or you can do it this way. It just goes back and forth with red and blue, red and green, red and green, red and green. Either way is a fine tactic, just whatever one you think will speed you to the conclusion fastest. So let me turn this off. You can always tell the two difference because they have larger nozzles. I'll mention that another way. Make sure it's off, plug it in, turn it on, make sure it's aligned. One way is to just move the relative length, and you should see it not have too much further out. We'll again adjust it ever so slightly. And it doesn't really change much, so there's fine. Now, having this here, as you can see, we didn't do too much, but my original markings are still here. Now the green's at a different location, so let's wipe those off. This is why there's a second marker color here, so that you can use one color for the red lighting and one for the green lighting in case you go back and forth that way. But so you use the second one, you can leave those there just so you can kind of see the comparison. And again, gently mark that spot as accurate as you can. The best way to tell that it worked is that you cannot see the marking because the light's too bright. Okay, so in this case, if you look way out here, you can see very faint colorings of this one. Less obvious on this side, but it's a little bit more faint noticeable over here. So I'm going to move this closer. It doesn't have to be at this distance. This is to get the ratios. We're looking at the ratios between this and this. The triangle remains unchanged. And I'll just adjust this so that these marks are right on my just now marked positions. That seems to do it. I've confirmed they're on both sides. Now, those are now actually, this is Y1 on the left and Y1 on the right. This is Y0, Y1, Y2, Y2. Okay? And this is for the green. The red didn't have it, probably because it was just not intense enough. But in this case, it's good. Let's go take a look. Come over here to this, and I'll do the same calculation I did a few minutes ago. Copy. Our position is different. We'll mark those down in a moment. But my position now is 14.7. We'll call it 14.7 on the nose. That's fine. That gives us 0.147 decimeters. Now we're ready to measure these points, but I now have enough points to mark here. You have to just see this for yourself. It's complicated to get the camera angle here. But, and you can just mark it on here. There's the blue. That's about 4.1 centimeters. This one is I'm going to have to say 9.55 centimeters. And then over here, 4.1 again. That's nice. It's reinforcing, right? This one's 9.6 centimeters. Probably 9.60, but we're not. When you do the tables, we'll talk about those. So as you can see, this is how I've marked it on my table. It's a little bit crooked because I'm not going very carefully with making sure this is crooked or whatever the case. It's really about where that center beam line, Y0, lands, crosses this black axis I've drawn. So these distances are relative to that point. So here we are, 4.10. Since I did make estimation on the other ones, I'm going to go and put it 4.10. This actually has presets amount. This is 9.55, and this one was 9.60. And now you can see that all my data is populated, so I've got a much better average. And if I put, I can't put If I put 650, I'm going to get the wrong answer because the back of this one is 515. So let's put 515. Not every one of them is the same, so double check yours. Again, we've got some large error, but let's take a look at our results here. Okay. As you can see, by changing the diffraction grating, I've changed the number of beams or lights that have shown up on here. Best thing that you can do for yourself, especially if time gets short, this should not take too long once you start getting the hang of making the measurements and using the spreadsheet. But if you do get short on time, just get the data points recorded from make the dots on here, make the markings, get as many as you can, and get them onto your spreadsheet, and then take a look at the results later. Once you've got your data collected, go over to laser comparisons, and you can see that the graphs have been prepared for you and show the red and the green data points. Now, as far as accessibility is concerned, you can do various things to change these from the colors that you see there so that they are more, let's say, stand out better in different color gradations. However, fundamentally, that the red and green have different connecting lines here. And we could change this. Let's say we rewrite this, right click on this, format data series, and then we come over and change the line from a simple green dashed line. Let's say for this one we would change it to the dotted line. So now again, that's a distinction between those two lines. That's something that you can do. And all we're seeing here is that the actual data points connected with lines that just guide the eye and how they compare to the actual wavelength that we see reported on the devices. But this is something that you can take a look at. You look at trends in the data as its diffraction grading lines for the diffraction grading density. As the diffraction grading density increases, how would you discuss these, say, trends in the data? By comparison, you just take the inverse of that, and it gives you the width of the distance between each slit, and that's the width D that is in the lab manual, and you can see this is plotted the wavelength versus that. I elected in this case not to include those reference points, but you can add those in fairly easy with this data and make discussion points about that as a factor of the slit width or slit distance D. Well, that does it for this week's walkthrough. I'd like to thank once again MathBar for joining us, walking us through a little bit of the theory. Hope everybody have any questions. Make sure that you ask your TA, your learning assistants. You can even ask me. And for now that you're ready to go, why don't you everybody come on and let's all do the wave. See y'all in the lab.
Basketball, soccer field. Looks like a wave when the people stand up to cheer out their players.
Hey everybody, how you doing today? I'm Dr. T. I'm joining you, and that's the first outtake of it. And then you perform the analysis. Okay, so in this week's lab, oh, that would be so funny if you were off to the side and you came in and you did the third one. Would you be willing to do that?
No problem. Like this?
Yeah, like this.
Like this.
So here we go. Okay, so, all right, everybody. Thank you very much for joining us this week's walkthrough. I hope that you find the lab to be fairly straightforward to walk through, and we can go out there and learn a little bit more about the wave. That was terrible, so I'm going to do it again. Once you've got your experimental once you've got your experiment set up in an ideal fashion, you can go and make your measurements, and that's going to be. Repeat this process for. Simply repeat this process. Oh, I love it. You guys are great. All right. And give you the same values. I'm probably going to not keep that part, but okay. That's it. See you guys in the lab.